My name is Dr. Ken Gallardi. Today I want to show you how the model of the complete photon that I described in an earlier video explains polarization interactions. I'll use it to explain two experiments, one a fairly simple one just using a polarizing film, and the second one using a birefringent media where the direction of the photon travel is perpendicular to the optic axis. I suggest that the latter is another litmus test of the credibility of the model. So let's begin with the linear polarized photon hitting a linear polarizing film whose axis of polarization is at an angle theta with respect to the polarization of the photon. And review the outcome when done one photon at a time. So first, we cannot treat the fields as vectors that can be resolved into components, for that would imply that a portion of the photon is absorbed and a portion is transmitted, which would violate quantization. That picture is often presented, but a photon-by-photon treatment makes that picture invalid. Instead, one recognizes that the photon is either transmitted in totality or absorbed completely, and one can't predict whether a given photon will be absorbed or transmitted. Yet, after a large number of photons have been incident on the polarizing film, the fraction of the photons that are transmitted is always the same. And that fraction is given by the law of Malus, as shown, where I sub t and I sub I are the transmitted and incident intensities. Again, this is consistent with the property of the total photon model, which says that all photon interactions are described by a probability mechanics. So while we can't be certain about an individual photon being transmitted, we can be certain that after a large number of photons have struck the film, that the fraction that pass will be the same from experiment to experiment and will be given by cosquared theta. Cosquared theta is the probability that a given photon will have its polarization reoriented in keeping with the polarizing film and be transmitted. I suggest this should be seen as another interaction that provides more validation to the probability mechanics inherent in the model of the complete photon. Now let's consider when a linear polarized photon, where the polarization is either parallel to or perpendicular to the optic axis. And experimentally, this is the orientation used in a quarter wave plate and is used to obtain circular or linear polarization. And it's observed that if linear polarization is obtained, then it may be different than the polarization of the ordinary or extraordinary rays, which are characteristic of the birefringent medium. It is also noted that the index of refraction for the polarization that is parallel to the optic axis is greater than when the polarization is perpendicular to the optic axis, implying that the two polarizations travel at different speeds. It's further noted that one does not get two beams with polarizations that match either the ordinary or the extraordinary rays. The explanation that the complete photon model gives is on a photon-by-photon basis, by imagining that the birefringent media impacts the photon and causes two things. One, different shells take on different polarizations of either the ordinary or extraordinary ray, so that each shell is traveling at a single speed and is therefore stable. The diagram you see shows the cross-section of a photon, showing the orientation of the fields for two different shells. It's noted that the fields are zero at the fault surfaces, separating the shells, allowing for a smooth transition in polarization direction. And the second impact for the perturbation is that the different shells take on different Bessel function magnitudes, so that the orientation of the initial polarization of the photon is captured. It is also noted that the model asserts that causal uncertainty, which is the consequence of quantization, prevents one from identifying specifically how the revised magnitudes capture the initial polarization. The result is that the shells split along the fault surfaces because of the different speeds of the different polarizations, although the shells continue to be moving collinearly. And when the photon is no longer impacted by the perturbation, it will return to the unperturbed photon configuration described as shown, which we describe as a single Bessel function, single sign function, and a single polarization. The polarization will be a combination of the polarizations of the two shells, although the causal uncertainty imposed on the model by quantization prevents us from identifying the sequence in which the photon regains its unperturbed format. Please note that the polarization shown is generic rather than specific for a given initial polarization. But if the outcome were linearly polarized, along the x-axis for example, then both beta and gamma would be zero. It's predicted that this reunion will be accomplished in the equivalent of a Fresnel zone after the photon is released from the birefringent perturbation. Then one is left to use pattern recognition to predict the outcome for each initial polarization orientation because of the causal uncertainty. So it's suggested that the shell structure of the photon allows for a reasonable explanation of how a single photon may respond to a birefringent media, giving greater credibility to the shell feature of the complete photon model. Thanks for watching. My next video will deal with momentum issues, and I'll look again at the storyline of the Compton effect. Please subscribe to the channel, please leave your comments, and please pass it on to others, particularly those in the physics community. Thanks again for watching, and God bless.